Hello, this is Physics Core Prep 7 on Euro 2. It should have been presented on the 14th of February 2018. Unfortunately, there were technical hitches, which I apologise for. I have now recording it in Camtasia and will make it available as an MP4 file on YouTube, so anyone who's interested can access it. Question number 1. How much of the incident radiation in a skull radiograph is likely transmitted to the image receptor as a percentage? Obviously, you start with 100% incident on the patient. You should pause your video, your MP4 file, until you are ready with the answer. And the answer is that when you go through about 10 centimeters of tissue for a typical X-ray beam, you're down to 10%, because the attenuation is exponential. When you go another 10 centimeters, you're down to a 10% or 1%, and that's a good ballpark numbers. We assume that 1% of the incident radiation is transmitted through a typical patient. Sometimes it will be a bit more, sometimes it will be a bit less, but 1% is a great answer. 10% is too much, 0.1% is too little. Just remember the 1%. What's the most likely grid ratio for a skull X-ray? Less than 10 to 1, 10 to 1, more than 10 to 1, or maybe because you're having bone, then no grid is actually used at all. The bone will attenuate, absorb X-rays, and thereby generate little scatter. And the significance of 10 to 1 is if you were doing an abdomen, the grid ratio is typically 10 to 1. If you're curious what the number means, is the length, the T, is about 1 millimeter, the gap is about 0.1 millimeter, and the ratio of the T over the gap D is about 10 to 1. So pause your videos, and the correct answer is you would use the same grid ratio in a skull X-ray as a chest X-ray, as an abdomen X-ray in a normal size adult, and they're all typically 10 to 1. It's a great number for just about all of adult and radiography and fluoroscopy. How will increasing the tube voltage in a skull radiograph most likely affect patient dose? Will it go up? Will there be no change? Will it go down? The implication is that with most of radiographic imaging, we have automatic exposure control. So pause your video. And the correct answer is when the X-ray beam penetration goes up, then we keep the radiation at the green image receptor constant. Because it's more penetrating, I need less, therefore I reduce the dose. And because the energy is higher, you always reduce the amount of contrast. And so the correct answer is you will reduce patient doses whenever you use high voltages, but remember you also reduce the image contrast. What's the likely effective dose for a skull X-ray examination? Giving you 4 options: very low, less than 0.1 millisievert, low, 0.1 to 1 millisievert, moderate, 1 to 10 millisievert, or maybe it's on the borderline between very low and low, something of the order of 0.1. And the correct answer is it actually is about 0.1. If you answer very low or low, I'm happy with both of those answers. If you answer A or B, I'm even happier. And you should remember that just about all radiographic examinations are either very low or low. Chest X-ray would be very low, and abdominal X-ray would be low. Don't get bogged down in the details. What's the likely cause of the white spots shown in a red circle on this skull X-ray? Ghosting, barium contamination, a faulty detector, or aliasing? Pause your WebEx recordings. And the correct answer is because they're white, they absorb the radiation that's incident, and they're little spots of barium contamination that's dripped onto a sponge and was used to support a patient's skull. In neurofluoroscopy, how do grid ratios compare to those of radiography? Are they higher? Are they comparable, or are they lower? Nice simple answer. Again, what the grid ratio is. Pause your recordings until you have the answer. And the answer is radiography or fluoroscopy. It really doesn't matter in terms of the amount of scatter. It's the voltage and the body region that determines it. We just use typically 100 times more radiation, higher tube currents in radiography, and the grid ratios are essentially the same. What is the most likely number of TV lines in a fluoro image? Your options are 125, 250, 500 or 1000. Pause your video recordings until you have sussed this one out. And the correct answer is that would either be 500 or 1000. We don't have 250 line TV systems, and although you could do 1000, there's really no need, and I would expect it's typical of a TV frame to have 500 lines and maybe 500 pixels along each line, and so the size of the image is comparable to a CT, and the amount of detail that you can see in a fluoro last image hold image is comparable to a CT. What's the most likely value of the exposure index in IR at US academic medical centers? Here's an example of an exposure index. The question relates to a body part, so this is a little bit of a red herring, if you like. Your options are 3, 30, 300 or 3000. Do you have any idea? You should. A good PAC systems will show you the exposure index. It's the number I'd be interested in. So pause your WebEx recordings. And the correct answer is most of body radiography is done with an exposure index of 300. If you use 30, you'd have too much mottle. If you use 3000, your patient would have received far too much radiation. How many photospot images could reach the cataract threshold dose? 5, 50, 500 or 5000 images. So pause your WebEx recordings till you have figured out the answer. And the answer is 500. The entrance radiation dose for one radiograph is about a milligray. If you have 500 images, you can get up to 500 milligray, and it is currently believed that the threshold dose for inducing cataracts by radiation is in fact about 500 milligray. So a lot of information there. If you put that all together, well done. Which type of detectors exhibit pincushion distortion during fluoroscopy? An image intensifier read out with a television system, an image intensifier read out with a newfangled CCD, a charge coupled device, a flat panel detector, or A and B. Here's just an example of pincushion distortion. So pause your WebEx, your video until you have the answer. And the correct answer is A or B. It is a property of the image intensifier. The input surface is usually curved, the output is flat, and when you try to squash a curved input onto a flat output, you will get this type of pincushion distortion. Increasing which would likely reduce CT beam hardening artifacts. Here's an example, the blacker area behind the bone, that's a beam hardening artifact shown by the white arrow. Can you reduce this by having more filtration, higher voltages, bigger focal spots, or possibly A and B, more filtration or higher voltages? So pause your video recordings, and the correct answer is you reduce the beam hardening artifacts by using lots of filtration and high voltages, and that's why CT is generally performed with lots of filtration and at relatively high voltages. Typical range would be 80 to 140 kV. What are the X-ray attenuation differences between grey and white matter as a percentage? Less than 1, 1 to 3, 3 to 10, more than 10. Grey matter looks whiter on the CT image because it attenuates more radiation. But how much more? These are your options. Pause your videos until you're ready to proceed. And the correct answer is it's typically about 0.5% or 5 Hounsfield units. Grey matter might be 40 and white matter would be about 35. What is the most likely volume CTDI for a routine adult head CT? 15 milligray, 30, 60 or 120 milligray? Pause your WebEx recordings till you're ready to proceed. And for an adult, I would expect it to be about 60. For an infant, a young child, maybe 30 would be more representative. If you're exceeding 80 milligray, you would fail the ACR-CT accreditation. You would not get the accreditation because your dose would be too high. What is the most likely dose length product in a head CT? 10, 100, 1,000 or 10,000? You should be looking at these numbers on a routine basis. At the end of every CT examination, there's a dose summary sheet. Pause your WebEx recordings, your video recordings, till you have figured out what you think is a reasonable answer. And it has to be like 1,000. A typical CTDI ball might be 60 milligray. Scan length might be 16, 18 centimeters. You multiply those two together, you get 1,000. 100 is way too small. 10,000 is way too big. If you can't get this question correct, you really don't have much idea of the appropriate amount of radiation, and my advice is learn it because it's the kind of question that will come up on the core exam. A head CT has an effective dose equivalent to how many years of natural background radiation? Is it like 0.01 years, 0.1 years, 1 year or 10 years? Pause your video recordings till you have the answer, and the correct answer is natural background in the years about 3 millisieverts. A head CT for an adult might be 1 to 2 millisieverts. A child would actually be similar because the radiation used is less, the conversion factors are more, and those two cancel out. 10 years is way too big. 0.1 is way too small. It is something like a year. When can a strontium-82 rubidium-82 generator be used again following an elution? After 5 seconds, 5 minutes, 5 hours or 5 days? So let me tell you about strontium-82. It has a half-life of nearly just over 23 days. Decays by electron capture to rubidium-82. That's a positron emitter, and the half-life of the rubidium is 1.25 minutes. So those are the important facts. Pause your videos until you figure out what you think is the right answer. And if you picked 5 minutes, you are correct. It is always 4 times the daughter half-life for equilibrium to be established, and another elution can be performed. For technetium-99m with a half-life of 6 hours, you have to wait 4 half-lives or 24 hours or a day for it to be eluted again. What type of detectors are used in PET imaging systems? Photoconductors, ionization chambers, scintillators, or photostimulable phosphors. So these are the options that you have. They're the type of detectors. Pause your record your videos until you have the right answer, and of course the correct answer is scintillators, things like bismuth germanate, BGO, is a scintillator, and all the other detectors are also scintillators. In a PET detector, we wouldn't use photoconductors, ionization chambers, or photostimulable phosphors. What's the benefit of using free gamma cameras in a SPECT system? Do you get better resolution? Do you get higher contrast? Do you get better sensitivity? Or do you get fewer artifacts? These are the 4 key issues in any image in terms of image quality aspects. Which of these is the important one? Pause your videos, and if you said higher sensitivity, you would be correct. With 3 gamma cameras compared to 1, you're going to get 3 times as many counts in a given time. The resolution and contrast don't change, and actually when you have multiple detectors, you're more likely to get artifacts rather than less likely to get them. What type of radiation detector is likely found in a nuclear medicine department? The picture here shows you a dose calibrator to measure the activity before it's administered to the patient. But will you also find a Geiger probe, an uptake probe, a well counter, or all of these in a typical nuclear medicine department? Pause your videos, and the correct answer is you certainly find a Geiger counter to monitor yourself for contamination when you leave a radioactive area. You would use an uptake probe to monitor the activity in a patient's or an operator's thyroid, and a well counter might be used to do pulse height analysis on contamination samples to see what kind of contamination you might have. What is the threshold amount of iodine 131 for discharging a patient in megabecs? And so, is it 1 megabec, 10 megabecs, 100, or 1,000? If you want to become an authorized user for the Nuclear Regulatory Commission, then you have to pass something called the RICE exam, radioisotope safety examination. It's certain questions on the core exam. If you do pass the RICE exam, your certificate will say authorized user eligible. If you want to become authorized user, you have to be able to answer questions like this. And if you're not sure how you're going to learn the answers to these questions, the answer is read chapter 13 in Mettler's book, the 6th edition on nuclear medicine, and you will sail through that exam. So if you haven't got the answers yet, pause the video, and the correct answer is about a gigabec or 1,000 megabecs of iodine 131. In the old units, that's about 30 millicuries. Which will affect T2 star? Susceptibility differences, magnetic sources like clots or hemosiderin, magnetic field inhomogeneities, or all 3. So here's the free induction decay signal. Normally, in the absence of T2 star effects, will decay exponentially with the time constant T2. There are T2 processes. Which ones are they? Pause your recordings, and the correct answer is susceptibility differences, magnetic sources, and magnetic field inhomogeneities are all examples of things that contribute to T2 star. Which is the frequency in code gradient direction in a head MRI? Is it the axial, the sagittal, the coronal, or is any direction possible? So here are the various gradients that you can have. Pause your videos until you can answer the question. And of course, gradients are vectors. You have 3 sets of gradients, so you can arrange your vectors to give you a net vector along any direction. It's a trivial engineering undertaking. How will the addition of gadolinium affect spin lattice interactions? The point about gadolinium is it's got a number of unpaired electrons. Each electron has a very powerful magnetic field. So when you put this into a patient, and it interacts with adjacent spins. Will the spin lattice interactions increase, not change, or be reduced? Pause your video, and the correct answer is you get more interactions, so T1 goes down. That's the secret to understanding these issues. When you have more interactions, T1s go down. When you have fewer interactions, T1s will go up. What type of, or which type of sequence is most likely to result in bounce point artifacts? Here's a very nice example of bounce point artifacts. Do you think this type of image is likely to be a spin echo, gradient echo, inversion recovery, or echo planar? While you ponder that, just pause your videos until you have the answers. And the correct answer is it's always in inversion recovery. It's as the magnetization decays and goes through the zero value, that is the bounce point that you have, and you will only see it in inversion recovery. Increasing which parameter is most likely to correct this aliasing artifact? Field of view, matrix size, gradient strength, or slice thickness? Let me explain why I know that it's an aliasing artifact. The magnetic field at the nose happens to be high. Because it's high, the Lamont frequency is big, it's a high frequency. If you sample it inadequately, you think you have a low frequency and put it where the low magnetic field is low. So this is the phasing cogradient direction, this is the high magnetic field, this is the low. Pause your videos, and it is increasing the field of view. You're essentially reducing the magnetic field, you're reducing the Lamont frequency, and the wraparound artifact, as it's often referred to, will disappear. Which has the highest ultrasound velocity? Is it fat, fluid, tissue, or bone? Pause your videos and I'll give you the answers. And the correct answer is soft tissue is a certain value, air is a lot less, bone is a lot more, and fat's a bit less, maybe a few percent. And that's all that you need to know. It's the relative values, the relative sizes. Don't memorize a pile of numbers unless you're a physicist. And it is bone that has the high velocity, air that has the low velocity, and a tissue is somewhere in between. How do images likely appear when depth gain compensation is switched off? It is sometimes known as time gain compensation or swept gain. Will they look brighter? Will they look pretty much the same, or will they look darker? So I'd like you to pause your videos, and the correct answer is when you switch the time gain compensation off by moving these toggle switches to the left, the image will look darker. That's what the time gain compensation essentially does. So the correct answer is darker. How will doubling the pulse repetition frequency of a 3 MHz probe affect its operating frequency? Will it increase? Will it be no change? Will it be reduced? Pause your videos while you're pondering. And the correct answer is if you increase the pulse repetition frequencies, you're essentially reducing the listening interval, but you don't affect the operating frequency. So there is no change. It is a reduction in imaging depth because you're sending out more pulses, therefore listening for a shorter time. And so the correct answer is no change. Which intensity is normally used to specify the intensity of a clinical ultrasound beam? Is it the spatial peak? Is it the spatial average? Is it the temporal peak, or is it the temporal average? So here's the spatial peak, here's your spatial average, and you can do the same for time. And pause your videos. And the correct answer is spatial peak temporal average. Why? because that is the best indicator of temperature rises, and that's one of the things, or one of the concerns that we might have in ultrasound imaging. At a 4 megahertz fundamental frequency, which frequency is likely used in harmonic imaging? Less than 4, the same, 4, 8, twice the frequency, or 12, 3 times the frequency. So pause your videos, and the correct answer is twice the frequency, although there are 12, the next harmonic is available, theoretically could be used. High frequencies are attenuated to a very large extent, and so it becomes unpractical. And so harmonic imaging for a 4 megahertz probe would be done at 8 megahertz. And that brings us to the end of the course. So if you listen to this presentation, drop me an email. I'll make sure that we mark you as being present. If you give me your nominal score, I will record it. At the end of the review course, I provide a summary of both attendance and scores to your program directors. So it's something that I think you might be interested in doing.